Alright guys, so just to recap our last video, we talked about approximating the area under a curve. We called this technique a Riemann sum. We had a left hand, a right hand, and a midpoint Riemann sum. But basically it dealt with just drawing a number of rectangles underneath a curve between a couple x values, which we call a and b. Those are the x values. Okay. And we tend to use lowercase n to represent the number of rectangles, but a lot of times we'll use the word subintervals. Okay, so we can say that as n approaches infinity, in other words, if we were to draw an infinite number of rectangles, then what's going to happen is we're going to see our wasted space either below the curve or above the curve minimized, so our area approximation is going to be approaching the exact area. Okay, so the more rectangles we draw in, the better the approximation. Okay? Alright, so we've been talking about finding approximate area underneath the curve. We're now going to switch our focus and talk about exact area under a curve. So first of all, let's suppose our curve is above the x-axis. Okay, so f of x is greater than or equal to 0. So right now we're talking about curves that are positive and not below the x-axis and negative. Okay, we'll get to that later on. So the exact area, so we're not talking about an approximation anymore. We're talking about the exact area under the curve from x equals a to x equals b is called a definite integral. And we use this notation down below to express it. Now each of these parts has meaning, so let's jot down what each of these parts represent. Alright, so make note of these different parts here. So first let's start with what we call the integral symbol. This looks like a capital S that has been stretched vertically, but it's not really an S. Okay, so that is our symbol for what we call an integral. And then down at the bottom we call this the lower bound. Sometimes we call it the left bound since we're talking about an x value. Alright, it's going to be the smaller of the two bounds. The number that you see on top of your integral, we call that an upper bound, or sometimes we refer to it as a right bound. The function itself is called the integrand. Alright, it's what we're actually going to be integrating. And then this dx piece on the end, that is just identifying the variable of integration. So usually it's going to be an x, but if our function was all in terms of p, then you would see f of p and then dp. If our function was all in terms of c, you'd see f of c and then dc. So it's really just identifying the independent variable. Alright, let's look at an example. Suppose we wish to evaluate the following. We see a definite integral. It's a definite integral because you see numbers here. You see a lower bound of -1, an upper bound of 3, and then the function itself is just 6, and then you see this dx on the end. Okay, so x is our independent variable. Notice there's no x in our function. So to figure out what this is equal to, it's helpful to be able to visualize this. So the function that we're talking about here is 6. So this is really f of x. So if we were to draw y equals 6, we know that's a nice horizontal line. What this means, this whole idea of an integral from -1 to 3, what that means is we are looking to find the area underneath that curve from x values going from -1 to 3. So we're looking to find, and if you have a different color, use it. We're looking to find this area. Alright, the area bounded by x values of -1 and 3, the x-axis, and then up to the curve y equals 6. Well, we can see this is a rectangle. And this area here, it's not difficult to find. Alright, the width here from -1 to 3, that's 4, and then the height would be 6. Not drawn the scale, but you get the idea. So our area here would be 24 square units. Okay? Now, the calculator, so this is equal to 24. I want to tell you how to use the calculator to do this. A couple different ways. Alright, so two things to do in the calculator here, and it's really important that you have a calculator in front of you. If you don't have one in front of you, you need to go back and watch this video later on with a calculator in front of you to make sure you're getting this down. So It's helpful to know both of these techniques. So if you were to press Math and then number 9, you're going to activate FNInt, all right, on your blank screen, okay, on your home screen. And if you have a newer operating system, you're going to see what I have here in blue, okay? And it's pretty self-explanatory. You're just going to put in the lower and the upper bounds, which, by the way, sometimes we call those lower and upper limits. Here you'd enter your function, which in our example up above would just be 6. And then you see another box here to fill in. That's where you'd have to enter in an x. So if you do it on our example up above here, you would see 24. Okay? Another thing to do. Right now, go to y equals. Okay? And I want you to enter in the function. Right? Our function here is just a nice simple 6. So you would enter y equals 6. All right? And then exit out of there. So from there, you would then go to Second Calc and then select number 7, which looks like this. You have the integral symbol f of x dx. What you'll notice when you hit that is it'll graph y equals 6 for you. So it'll graph your function, and then it'll ask you for the lower limit and then the upper limit. So when it asks for the lower limit, this is where you would enter -1, hit enter. It'll ask for the upper limit, enter 3, hit enter. And then you'll notice that it actually gives you not only the area of 24, but it's also going to shade this region here, which is giving us or showing us where that area of 4 is located, or that area of 24 is located. Okay, so be aware of each. You don't always have to do it this second way where it gives you the visual of your area. Okay, and again, it'll shade it for you. Okay, but usually we're going to just go to Math 9 and use FNInt, but there may be times where it's helpful to see the graph in the shaded area. So just be aware of both. Okay, next example here, we're looking to evaluate this definite integral from 0 to 3, and we see the function is 6x. So what this really means is we're trying to find the area underneath 6x from x values ranging from 0 to 3. So if we were to graph y equals 6x, all right, we know it's a line, it's pretty steep, and we're looking to find the area bounded by that function, the x-axis, and then x values going from 0 to 3. So we can see that it's making a triangle here. Now, at the top of this triangle, right, this would be the point 318, right? So from there, if we're trying to find the area of this triangle, well, think about geometric formulas that you know. We know 1/2 base times height. Okay, so this area can be found by doing 1/2. The base would be 3, the height would be 18, right? That 18 is just the y value on that function. That is going to give us an exact area of 27, okay? So when we evaluate this, we get 27. So this number represents the area underneath the curve. And recall that this curve here, we're only looking at examples right now where the function is positive, meaning it's completely above the x-axis. Well, what if it's not completely above the x-axis? That's what we're going to explore next. All right, take a look at this next example here. We're looking at a definite integral from 1 to 3, and the function this time is -6. So if we sketch this, we can see it's completely below the x-axis. So the function is negative. Well, because that function is negative, it means that in this region here, between 1 and 3, we're going to have some y values that are negative. So when we look to evaluate this definite integral, okay, since we have a rectangle here to find the area, we know we're going to do base times height. So the distance from 1 to 3 we know is 2. But then the so-called height, or the y value here, this y distance, because these y values are negative, right, because this point on this curve is a negative y value, that means we would have to put a -6 in here, okay, because, again, the y values are negative. So we say that the definite integral would be -12. Okay, think of it as that area is below the x-axis, so we say the definite integral would be -12. All right, however, or but, all right, the actual area of that region would just be positive 12. Okay, so we know we can't have a negative area. That wouldn't make sense. Okay, area can only be positive, but because it's located below the x-axis, in the definite integral, it's going to show up as negative. All right, again, that's because the y values on the function here are negative. All right, so now let's generalize here. So we can say that if our function is less than or equal to 0, so meaning it's below the x-axis, okay, so it's below the x-axis, then the definite integral here is always going to end up being the negation of the actual area. So up above, we know the actual area was 12. Notice how the definite integral was negative 12. Or we can kind of work backwards here. We can say that the area itself is equal to the negation of this definite integral. So the definite integral we know is going to be negative. So if you negate a negative, you get the positive. Okay, so that's just a way of generalizing what we just talked about. All right, last example here. So now we're looking at the function 6x like we saw earlier, but this time we're not just going from 0 to 3, we're going from negative 1 to 3. So what this really means is we're trying to find the area bounded by the curve, the x-axis, and these bounds of negative 1 and 3. So what we really have here is we have a couple triangles. One is above and one is below. Well, we saw earlier that the area from 0 to 3 underneath 6x was 27, right? We saw that in a previous example. Now, this other triangle here, if we were to look at the coordinates of this point, this is negative 1. If I put negative 1 into the function, I get negative 6. Okay. Now, the area of this triangle down below here would be 3. But remember, because it's down below, that's technically going to give us a negative in our definite integral. So when we look to evaluate this, we really have 27 up top, but then take away that 3 in the bottom, it's going to leave us with a net area of 24. So please understand that these definite integrals will give us a net area. So that means anything below will be subtracted from anything that's up above. Okay? If you were to throw all of this into your calculator, you would see that it's going to give you the net area. Now, what I would like you to do is put this into your calculator. All right, same exact thing, but now put an absolute value symbol around that. Well, the absolute value symbol is going to make sure everything is positive. So this region down below, it's really going to be reflected over that x-axis. So graphically now, if that were to happen, we would be looking at an area that is all positive. So we would have 27 plus the 3, which would give us a total area of 30. So please make note that this is known as the total area, whereas the definite integral gives us what we call a net area.